Hello, this is chapter 4 for the Top Hat Organic textbook. With that, so for this one, we're going to be talking about acids and bases. With that, so acid-base chemistry, it's a little different than, it has some similarities to what you did in general chemistry, where we're going to be talking about Lewis acids and Bronsted-Lowry acids. With that, but we're not going to be doing any calculations with that. But acid and acidity becomes incredibly important in organic chemistry because of the ability to be able to remove hydrogens from organic molecules. And so one of the things that we're going to be doing in this chapter is talking about acidity, what makes some hydrogens in organic molecules more acidic than others, and being able to determine what the most acidic hydrogen is. With that, so the first thing we have to do is we have to talk about the Bronsted-Lowry definition. And for this one, they came in and said, okay, we're just going to be looking at an H+. So an H with a hydrogen or with an electron removed is just a proton. So sometimes an H+ is just called a proton. So if it has an H to donate, so just like HCl, right, hydrochloric acid, right, it has a hydrogen to give away. If you accept that that hydrogen, right, then you are you're a base, right? So with that, right, we're going to have this. This is a right. So this is a partial negative, partial positive, right? Partial positive, right? It's going to want a partial positive, partial negative. Right? These electrons are going to want to make a bond to that hydrogen, right? Because partial negative attracted to the partial positive. These electrons have to do something, and so they're going to be pushed onto those electrons, right? Because hydrogen can only have one bond. Mm-hmm. So if you have a hydrogen to donate, you are an acid. But that if you grab the hydrogen, right, you're considered a base. Now, if we look at the product, okay, so what we have to imagine is if the reaction is going in reverse. If it's going in reverse, now this chlorine is coming in and let me do this in blue. Here, this is coming in and grabbing the hydrogen, pushing that back like that. And so here, the chlorine is coming in and acting like a base, and this hydronium is acting like an acid. And so what ends up happening is if you're an acid over here, the corresponding molecule over here, without the deprotonated version, is considered a base, and so, but it's we can't just call it base because we don't want to get confused on this side. So we call it the conjugate base. So if you're a base on here, the protonated version is a conjugate acid on the product side. So if you're an acid on the reactant side, you're the conjugate base on the product side. If you're a base, you're a conjugate acid. And so I think they did the naming just to mess you up, but in reality what it is if the reaction is going backwards, what's serving as the acid and base now, and we have to get a slightly different name to it to not be confused with the regular acid and base in the reactant side of the reaction. Okay, so if you're reacting in water, okay, so usually what's going to happen is if you're a stronger acid, what's happened is that your acid is probably going to react with the water to make hydronium, or your base is also going to react with water to make hydroxide. And so that's why a lot of the reactions are not actually, organic reactions are not done in water, because we don't want that reaction with them, stuff like that. But you can get that, stuff like that. So you have to be careful. Okay, and so what can happen is, right, so if you run a reaction, even if you put in molecules, so they're going to react with the water, and then the hydronium is actually going to react with the hydroxide, so that to make two versions of the water. And these guys here, the NaCl, is just going to be, they're just spectator ions at that point. Okay, so the other definition of acids was developed by Gilbert Lewis. He's the same one that developed Lewis structures. So he said, okay, we're being a little bit too narrow in this with Bronsted-Lowry. We can sort of expand the definition of acids and bases. And acids are things that accept lone pairs. while bases are those that have lone pairs to donate for that. And so in here, this has extra lone pairs. It's going to be attracted to the iron here. You can sort of think of this as a -1, -1, -1, and then this would be, say, a +3. Okay, so the electrons, right, are going to be coming in here and making this new bond here. So this lone pair here is going to be making the new bond. Okay, so this has a lone pair to give to here, but this is no different than what we had if we had, say, OH minus plus HCl, or plus HCl, right? This is going to come in, grab this, go, and the electrons are going to go away, right? This hydrogen, right, is going to be accepting the lone pair, this lone pair, from the Lewis, from this base. So the right here, let me actually draw this a little bit better. Let me draw this. So if you had OH minus, right, we had H plus going to HOH, right? OH minus is a Lewis base. It has lone pairs to donate. H plus is looking for lone pairs, and so it's going to make this new bond here. Okay. So it's just widening the. So if you're Bronsted-Lowry bases, they fall under this Lewis acid Lewis base. It's just other things also fall into it. Okay. So remember, for all of these, opposites are going to be attracting. Okay. So if you've got a lone pair here, right? So you've got partial positive, partial negative. The lone pairs have negative characters in them. They are going to want to form a bond to this partial positive. Same thing goes here. Lewis acid, whether it's a hydrogen or something like aluminum chloride, it's going to have a partial positive charge. It's going to be accepting those. These lone pairs are going to be attracted to here to make a new bond with that. So it doesn't have to be a hydrogen. Most of the time we're going to be dealing with this with reactions. We're going to be talking about Bronsted-Lowry, but there's special times where we're going to be dealing with Lewis acids, Lewis acid catalysts down the road. Okay, so just as a reminder, carbocations and carbanions, right? So these two electrons, right, if they go onto a leaving group to leave behind a carbon with 3 bonds, right, a carbon cation, so we call that a carbocation. If instead the electrons, right, these 2 electrons end up onto the carbon to form this new lone pair, now the carbon has a formal negative charge, and so it's a carbon, it is a carbon anion or a carbanion. So, okay, so we're going to be using those quite a bit. How about that? And so again, you've got carbocations, carbanions, right? You have something that's negatively charged is going to attack a carbocation. Or if you have a carbanion, it's going to be attacking something positively charged. Okay? Doesn't necessarily matter what it is. Okay, so we talked about this in the last chapter. If you've got electrophiles, right? So about that, so they are electron loving, right? So if you're loving electrons, you must be positively charged. So a carbocation is an electrophile. Okay? But if you have a nucleophile, okay, it's going to be some sort of Lewis base. So about that, you have a lone pair, right? You are nuclear loving, you are positive loving. So you must have negative characters. So you are going to come in here. You're going to have a lone pair to make a new bond to that carbon. The carbon can't have 4 bonds, so it pushes those electrons up the oxygen. But these two, that lone pair ends up forming that bond there, and this bond here, those 2 electrons end up forming this new set of this third set of lone pairs right here. Okay, so this is the extent of the calculations that we're going to be doing. stuff like that. So if you remember back for the a classic equilibrium constant, right? So it's the concentration of products over concentration of reactants, right? So we have products, we have reactants, and water isn't included in there because it's pure liquid. Pure liquids and pure solids, their concentrations don't change, so they are not part of the equilibrium reactions. So if we have this, then what we can do is we can this equilibrium constant. What we can do is take the negative log of it and be able to rank them. Okay, and we put the negative out here just so that the numbers end up being a little bit easier to deal with. We like working with positive numbers as opposed to negative. But the consequence of that is if you have something like this where you have a very strong acid like nitric acid, you do end up with some negative numbers. Okay, but what ends up happening is the way that we have the pKa scale going on here, the smaller the number, the more acidic it is. So hydrochloric acid is -7, nitric is -3, and so with that, so acetic acid is about 5, water is about 16, like that. So the large, the smaller the pKa, the stronger the acid. Now, if you remember, so if you're an acid on one side, on the product side, you're the conjugate base. So you can actually correlate the acidity strength with the conjugate base strength. So it turns out that if you're a very weak acid over here, the deprotonated conjugate base form, if you're weak, you're going to be strong, right? So water, not particularly acidic, but if you deprotonate it to form the conjugate base form, it's hydroxide, sodium hydroxide. That's the classic sort of base in everybody's organic or general chemistry lab. So right? So conversely, if you have a strong acid, so like hydrochloric acid, HCl, right? The corresponding conjugate base is deprotonated form is Cl minus. It's really, really weak base, right? So that's why you can hold a bunch of sodium chloride in your hand and it doesn't burn, right? Or you throw salt inside of your water when you're boiling up your mac and cheese, right? So you do that, right? Make it taste a little better. And also, a little salt in your pasta water. You put that in there, right? It doesn't change the pH, of the water, because this is a really, really terrible base, right? So as the stronger the acid, the weaker the conjugate base, and vice versa. Okay? And no, I'm not expecting you to know, have this memorized. But I do know the trends, right? So if I'm asking which is a stronger base, right? If I gave you the pKa's, if I gave you ethanol and hydrochloric acid, those pKa's, and asked you which one of the deprotonated form, which one's a stronger base, you would say, oh, weak acid, strong conjugate base. Strong acid, weak conjugate base. That's what you would need to know. Okay. So again, if you have, the protonated form, if you look at the pKa of that, the weaker the acid, the stronger its conjugate base. Okay, so now predicting, so you can come in and if you have the pKa's of the acid form on the reactant side and the conjugate acid on the product side, you can actually tell which way the reaction is going to go. Okay, and so it's going to go from a low pKa acid to a high pKa acid. Okay, so it's going to want the reaction is going to want to go up in value. Okay, and so for here, right, you've got acetic acid, you've got water, stuff like that, and so you're going from 4.76 to about 16, right? The reaction is going to want to go that way. Now, if you're thinking about, okay, how am I going to remember that? Well, think about HCl, right, plus sodium hydroxide. Actually, we'll just do OH minus, going to, right, Cl minus, going to HOH, right? Now, HCl is, right, this pKa is what? pKa, right? It's like -7, right? It's a strong acid, right? Water is a really weak acid, right? pKa of like 16, So if you know this reaction, you know this is going to go. So it tells you, where it's going to go, right? We're going to go from very low pKa to a very high pKa. You don't even have to remember the numbers, but you're going from a strong acid to a weak acid. So if you remember that reaction, this one works the exact same way. Stuff like that. It's just a little bit fancier of a molecule. Stuff like that, but the rules still apply. Okay? So for here, right? So for that, you're going from, so this is a general sort of. If this was pKa of 25 and this one was 35, right? The reaction is going to want to go that way. Okay? If this is 2 and this is 4, right? Again, it's going to go up. Doesn't matter, the order of magnitude. It just needs to go up. So it's going to go that way. Oop, excuse me. It's going to want to go that way. Here, we're going to go from 12 to 1, okay? So for that, and so really it wants to be on this side, right? So that means the reaction is going to go that way. Okay? Now, it doesn't matter about what the actual numbers are, okay? Now, the other thing is you have to be aware that if you had a pKa, say, -7, and you're going to go to pKa, to -5, right? So by that, so it's, you just say, well, it's going to go from 5 to 7. What's going to go that way? But they're negative, right? So this is a higher value than this. So in this case, the reaction is going to want to go that way. Okay, so it doesn't matter about the order of magnitude that you're dealing with. It just needs to go up. Okay, so just be careful. Okay, so one of the ways that you can do this, so you can take advantage of this in water solubility if you make your molecule charged. Okay, if you add an acid or add in base, you can actually go in and make it charged. So the classic example is benzoic acid here. So this is very insoluble in water. But if you throw in some base, the hydrogen is going to be removing the hydrogen from the carboxylic acid group to form the negative, the salt. Right? And so this is very soluble in water. Okay, so giving your inorganic molecule a charge actually makes it can actually make it much more water soluble. So if you'll see so you'll sometimes see that in a generic name for a drug, you'll actually see HCl. It's because what it's done is there's a nitrogen in there. You can put a charge on there, and it makes it much more water soluble. Okay, so the classic example is actually cocaine. So powder cocaine is actually in the hydrochloride salt because it needs to be soluble. So when you snort it, it dissolves in the water in your nose. But for crack cocaine, you don't want salts, right? So salts have a very high boiling point. Which is the reason why salt doesn't, evaporate. So it needs to be the free base for this, and so this one you wouldn't be able to. This is not very water soluble, but you can get into a form that can get that you can go in and boil it and stuff like that. And so this is a classic case, and they drug makers use this all the time. Actual pharmaceutical companies use this strategy all the time of being able to add a charge to the molecule. It doesn't necessarily affect the properties of the molecule. I mean, the pharmaceutical kinetics of the activity of the molecule, but it can improve the water solubility to be able to make it into a drug form, into a pill. Okay. The other thing, so next up is going to be being able to determine the acidity of the molecule. So if we have two molecules, can we tell which one is more soluble than the other? Okay. So the first thing we're going to have to do is we're going to have to figure out which one's the most acidic hydrogen. And it's almost always going to be a hydrogen that's not on a carbon. And we'll actually talk about acidic CH bonds at the end of this section. But for the most part, it's going to be you're going to be talking about acidic things that aren't on carbon. And it turns out that the atom that hydrogen is on, the bigger it is, like physically bigger it is, the more acidic that bond is going to be. So HF, HCl, HBr, HI, as you can see, the atom size gets bigger and bigger and bigger. As it goes up, it gets weaker and weaker and weaker because there's just a lot more distance between the nucleus and the hydrogen, so that to be able to, there's just so much fluff around there that you're not going to be able to think, there's just not going to be much holding that together. So if you have HI, you're having a very, very strong acid. So it's 1,000 times more acidic than hydrochloric acid. You always think of hydrochloric as sort of a classic, classic strong acid. HBr and HI are much stronger than that because the molecules are much bigger than that. It also turns out that as you go across the periodic table, so as you go, I should say, so for this one, as you go down the periodic table, down a column, the more it's going to be more acidic. So chlorine is going to be more, HCl is going to be more is going to be a lot more acidic than HF, right? Because chlorine is a lot bigger than F, right? This is actually, HF is considered a weak acid. Okay, so by that, and this works for any column. As you go down the column, it's going to be more acidic. So sulfur is going to be more, an SH bond is going to be more acidic than an NH bond, and a pH bond is going to be more acidic than an NH bond. As you go across from left to right, so with that, it also increases the acidity, right? So a CH bond in general is going to be pretty weak, not very acidic at all. But as you go across, right? So NH-OH and then HF, right? So with that, so as you go across, this is the electronegativity effect. So with that, so as you go across, the electrons are going to be wanting to spend more time on either the fluorine or the oxygen, so that weakens the bond. Okay, they're going to spend a lot more time on the fluorine than they are the hydrogen, or the oxygen rather than the hydrogen. So it weakens that bond, so it makes it more acidic. Okay, and so if you look at this, it's both electronegativity and size. Okay, so and again, you do not need to know these numbers, you just need to know the trends. And so when you're looking at the bond, what is holding on to the hydrogen, okay, that's the first thing you got to do. Is the closer that is to iodine on the periodic table, the more acidic it's going to be because it's bigger. It's because iodine is not only electronegative, but it's also really, really big. So that is an incredibly weak bond. Okay. So after that, okay, so for carbon, this comes into play with carbon mostly, is it turns out that so the amount of S character there is on the carbon, the more acidic it is. So, right, so this is an SP, right? So it's 50% S, 50% P, and so that turns out to be really, really, really a lot more acidic than if you had SPP, right? SP2, right? So that's only 33% S, 67% P. Right, and you're saying, well, it's only like half the pKa. Well, so this is only like twice as much. No. Remember, this is an order. Each one of these is an order of 10. So it's like 10 to the power 19, a 1 with 19 zeros, more acidic than ethylene. The double bond. If you go to sp3, right? SPPP, now you're only talking about 25% S character, something like that, and so you have even less, and so it's even less acidic. So that's a way to think about it. Okay. The other big issue after so when we're going to go down this sort of decision tree for this is what are called inductive effects, something like that, and so this is where if you can pull electron density away from that bond, so whatever that hydrogen is, it weakens it. The weaker the bond, the more acidic, the more easily things can get grabbed away. So like that. And so having electronegative atoms near the acid bond, the acidic bond, makes that bond more acidic. Okay, so remember this right here it would be CH3 COH. Okay. So this form here, so I drew this out, or I wrote it like this so you could, get practice in saying this. And so this one here has a fluorine on it, OH, right? So having something electronegative near, so this, right, we have a hydrogen that's not on a carbon, okay? So that's almost always going to be more acidic. stuff like that. And so they're both hanging off of oxygen, so that's a tie. But this one has an electronegative. Actually, this one has something more electronegative near it, and so this one is going to be more acidic with that because the electron density is literally getting pulled this way, getting pulled towards the fluorine, and so it weakens that bond because there just simply aren't as many electrons between the oxygen and hydrogen because they're getting pulled that way. Okay, and the more you have, and the more electronegative it is, then the more acidic it is, right? So we've got chlorine versus fluorine. Okay, the fluorine is more electronegative than chlorine, so like that. So this is going to make it more acidic. And you would say, wait, hold on, you just said the closer it is to iodine, the more acidic it is. No. That's just for this first thing. You're just saying where the hydrogen is. If the hydrogen itself is on an iodine or chlorine versus fluorine, then the molecule is more acidic. But that's not where this is, right? So here, the molecule isn't on the chlorine; it's on an OH, right? For both of these, CH2 fluorine, right? Right? The acidic hydrogen is here and here. That's a tie. They're both on oxygen. Okay, then it switches to electronegativity. Okay, fluorine is more electronegative than chlorine, so this one is going to be more acidic. Okay, so you have to think about this. Okay, go through your decision. We'll talk about all the sort of things in here. Okay. So inductive effects, so the more you have, right, the more acidic it's going to be. So if you have one fluorine, right, it makes it more acidic. But if you have 3 of them, it makes it even more acidic. So trifluoric acetic acid, this is considered a classic strong organic acid. So you see this quite a bit. Now, one of the things about it is proximity does make a difference. So if you have a chlorine adjacent to the carboxylic acid, right, you have a pretty good, 2.8. If you move the chlorine, over one more carbon, then that effect starts to wear off pretty quickly. So that because remember a normal sort of acetic acid is like 4.7, 4.8, something like that. And so we're not that far away. Something like that. But if you move the chlorine close, then you're getting 2.8, something like that. So you're 100 times more acidic than if that wasn't there at all. Okay. So the other thing is having a pi bond next to the acidic hydrogen is going to make a huge difference, right? So so you've got the hydrogen on the you've got an H that's not on an oxygen, and so that's going to be the most acidic. But for here, you've got the double bond O, and there's two issues going on here. The biggest one being resonance, and so if you deprotonate this, you can do a resonance structure where we put the negative charge up onto that other oxygen, stuff like that. And so it's the question of so if you're moving 100-pound box, right, stuff like that. So if 2 people are trying to move it, it's not too bad, right? 50 pounds apiece. But for ethanol, okay, if you deprotonate this, then all of that negative charge is going to be borne by by this particular oxygen, which again it's like having a 100-pound box. If only one person is moving it, it's going to be incredibly heavy. Okay, stuff like that. And so if the product, when we get to that point, if we can stabilize the molecule through resonance, that's very, very, very good. Okay, but there is an inductive effect, right? Because oxygen is very electronegative, right? It's right next to fluorine, and so you're getting the electrons pulled towards the oxygen. So by that you just have the one oxygen here. Here you have 2, and so again you're going to be pulling it through the inductive effects. Okay, but you can see this with something like cyclohexanol versus phenol, right? Having this pi bond immediately adjacent to the acidic, so this is the acidic hydrogen, with that. So having a pi bond immediately adjacent to it allows for this, having the negative charge that would normally be here also go here, here, and here. with that. And so now you've got several additional atoms being able to bear that charge. Okay. So here's the decision tree. So what you want to do is you want to identify the most acidic hydrogen, and most of the time that's going to be a hydrogen that's not on a carbon. Okay. But that. So when you do that, when you look at that, when you're comparing the two, so that the atom that's holding that acidic hydrogen, the bigger it is, the physically bigger the atom is, the more likely it is, the more acidic it's going to be. So you can see that the closer it is to iodine on the periodic table, the more acidic it's going to be. And so if that's a tie, so let's say they're both OHs, then we move down to the next one. But if you're comparing OH versus SH, right, SH is larger than OH, so the SH is going to be more acidic. Okay, so if we have a tie, then we're going to go down to the next one. Is there a pi bond immediately adjacent? Now, it doesn't have to be a carbon-oxygen double bond, but a carbon-carbon double bond, carbon-oxygen double bond, a sulfur-oxygen double bond, whatever, doesn't matter. If there is a pi bond immediately adjacent to it, that's going to be much more acidic than if there's not. Okay, so for that, if there's a tie on that one, then we go down again to see are there electronegative atoms near it. Stuff like that. So are there oxygens? Are there fluorines, chlorines, whatever? Stuff like that. So the more acidic it is, then the more you have, the more acidic the molecule is going to be. Okay. So for this one, did I talk about this? Okay. So if we're looking at something like acetic acid. So if we're looking at something like OH versus phenol, okay, the most acidic hydrogen is going to be this OH here, right? So they're both going to be on the OH, stuff like that, and so that's a tie. And so we come down here to say, okay, is there a pi bond immediately adjacent? Well, yeah. So there's a pi bond. Here's a carbon-carbon pi bond, and there's a carbon-oxygen pi bond. Okay, so that's a tie. And then we come down here, we're looking at, are there electronegative atoms nearby? Well, this one there is, right? There's this oxygen here. Here we just have regular carbons. So that makes this much more acidic. Okay, and so if we're looking at okay. And so if we're looking at SH versus like that, so if we're looking at these two, so we're going to look at the most acidic hydrogen, and so for this one, right, we're going to be looking at OH versus SH, right? So that's the most acidic, right? So SH is much bigger than oxygen, so it is going to be the more acidic molecule. So even though you got the fluorine here, that doesn't matter. This one is going to be a lot more acidic. Like that, so you just stop. So for nitro groups, right? So they are very electronegative. Stuff like that. So they are very an electronegative group, and they have this special thing especially with phenols, where you can have a because not only do you have this inductive effect, but if they're in the correct position, with that, and so if you have a nitro here, right, you deprotonate that hydrogen, the negative charge is gonna go here, here, and here. Well, oh yes, so here we go. Oops. Right, it's gonna go. It's gonna be there, 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 and there. Okay, but if it's in what's called the pair position, it'll also be ortho. It would also work. If you're looking at these, right, the negative charge is here, there, there, and there. And what can happen is, if you notice, there is a positive charge on the nitrogen of a nitro group. You can stabilize this negative charge and actually move this over to here. Okay, so you have an extra resonance structure compared to if it's in this position here. It's what's called the meta position. Again, we'll talk about that later. So with that, and so if the nitro is in a special position, it can give it an extra boost. So the more resonant structures you have, typically the more stable the molecule is. Okay? So solvents can have an effect, stuff like that. So if you can dissolve the molecule in the solvent, then it becomes much more acidic because it can be charged. Okay, and so remember when we talked at the very beginning that molecules, for organic molecules, if they strong acids, strong bases, they will react if they're put in water. And so what we need to do is we need to, we're going to need to use these things in things other than water, with that. And so we can actually, because the molecules themselves can be active acids and bases, stuff like that. And so if we have an alcohol, it's very similar to if you have water or hydroxide and things like that. It can come in and attack an acidic hydrogen, or even a C double bond O. This oxygen, right, has negative character to it. It can act like a base, right? So just like there's partial positive, partial negative, right? It can come in and act as a base. Okay? And so sometimes what we need to do is if we have an incredibly strong base, okay, something like the amide base here, so the conjugate base of ammonia has a very strong pKa. If we were to just dump it, if we had any water around, it would just react with water and leave hydroxide around. And so this is a much weaker base than this. And so sometimes we have to do is we have to run these in other solvents that aren't nearly as acidic. And so you can actually run it in ammonia. So even if this comes in and deprotonates the ammonia, you're just left with the NH2. Or you can run it into other sort of you can run it in, say, hexane or other sort of solvents like that. This is nice because we'll talk about protic and aprotic solvents later, stuff like that, but this is a particularly good solvent being able to use this reaction. If you have the hydride in here, stuff like that, so the T-butanol is actually less basic than other things, and so it'll actually come in here. So this is a stronger base, stuff like that, and so we can work with other sorts of things, stuff like that. So you can also run this if you had, say, this really strong form, a carbon nucleophile here, stuff like that. So a base, it's really strong, stuff like that. You're not going to be able to run this in water. You're going to run this in like hexane, which can't get deprotonated from this, or even if it did, it wouldn't matter because it would be very similar pKa. Okay. Now another thing to do is to think about this. So the amines work the same way. Amines and amides work the same way as phenols and alcohols and carboxylic acids, right? So this is the this one here is going to be they're all NH bonds, okay, but that, and so that's a tie. But these two, the anilines and the acetamides, these have adjacent pi bonds, okay, so these two are going to be more acidic than that one. But this one has the electronegative C double bond O, so it's the nitrogen version of a carboxylic acid, right? So for the same reasons, this is going to be more acidic than that, stuff like that. And so the nitrogen follows the same rules as for the oxygens. Okay. Now, one thing to note is that if this gets protonated, you can't go through this. You won't have the lone pair available to be able to do the resonance, stuff like that. So do be careful in that. So, okay. Thank you.